Let's get started and welcome you all to Thermodynamics 2.0 2025 webinar talk series. I'm Ram Podel, Assistant Professor at Appalachian State University. I coordinate Thermodynamics 2.0 Society's effort toward connecting dots of human knowledge in natural and social science. I invited Michael de Vrugt, a physicist and a philosopher of science, for this talk. Is thermodynamics fundamental? Welcome, Michael. Michael is Assistant Professor of Physics at Johannes Gutenberg University in Germany. Michael earned PhD in both Physics and Philosophy at University of Münster, Germany, and worked as a postdoctoral researcher at University of Cambridge. His research focused on nonequilibrium statistical mechanics, soft and active matter, and philosophy of science. It's good to see many physicists and the interdisciplinary researchers in the room. We are very excited to welcome you all here. Together, we aspire to take thermodynamics to next levels, thermodynamics 2.0, as we call it. I'm a mechanical engineer by profession. Obviously, thermodynamics is a subject near and dear to me. I always wonder about the complementary nature of physics and thermodynamics, especially given my background of research in thermal fluid energy theme. I have spent quite some time studying Navier-Stokes equation. To me, Navier-Stokes equation and the Klein-Gordon field equation are some good examples where physics meets thermodynamics. Is thermodynamics a science or an accounting tool? For many engineers like myself, thermodynamics is a universal science having jurisdiction in both closed and open systems. Thermodynamics utilizes intensive and extensive properties of system and surrounding. The language of thermodynamics is energy. Its derivatives such as entropy and power. A derivative with respect to space, the gradient of energy is force, and that with respect to time is power. Hamiltonian and Lagrangian are functions of energy. We may call them foundation of science, the application of which spans across matter, life, and evolution. Artifacts of universal science knows no boundaries, be it natural or social science or political science. Newtonian approach of classical mechanics is based on force and fields. We inherited this legacy and constitution. And physics is still attempting to unify sciences in terms of force. This is a long shot, given the history, current state of human knowledge, and science and technology. Energy framework unifies science at least at one scale. We may call it human scale. There could be many parallel threads as well, probably based on force and field. We don't know for sure. The state of our human knowledge is not there yet. Even 3 centuries after Newton's Principia, we have not been able to unify 4 standard forces of nature. We have spent too much energy and resources with much in terms of unified science of matter, life, and evolution. More is different. To copy Philip Anderson, partly our culture may be casting a shadow, or we have not learned lessons from a history of Newton's discovery, unifying terrestrial and the celestial mechanics. We know a lot about the physics of matter. However, physics of life evolution is yet a black box awaiting Newton 2.0. We need better methods, new methods more appropriate to the critical problem and the issues challenging humanity in our age. If we trace a root cause of physics, action principle lies at the heart of fundamental physics, from classical mechanics through quantum mechanics, particle physics, general relativity. Action principle starts with the energy function called Lagrangian, describing a physical system. The principle of least action gives verifiable answer for a conservative system at the least. As we know it, life evolution are not a class of conservative system. So are human and human society. We don't yet know much about the Lagrangian and Hamiltonian of individual in a society. Physics is yet to expand its scope and generalize its knowledge of matter, soft or active, to life. In the interim, thermodynamics aspires to fill this knowledge gap using its phenomenological approaches. Yes, we anticipate physics to catch up with the advanced knowledge and precise tools for analysis and measurement. I hope we can see that light during our lifetime. Coincident, this year, we are having two Michaels in row. Earlier, we invited Michael Parker from University of Essex. I guess, is Parker in the room? Let me see participants list. Michael Parker, are you in the room? Probably not.
Yes, to say I'm here. Yes.
Great to see you, Michael, here. You can find Parker's talk in our YouTube channel. Without further ado, I hand this floor to our invited speaker today, Michael T. Vrugt. Michael, please take it away. It's your time now.
Yeah, thanks for the invitation. I'm happy to see such a large crowd here. That, of course, gives me a responsibility to now live up to all these expectations. And I hope I'll be able to. Yeah, my talk is entitled, Is Thermodynamics Fundamental? It's partly based on the preprint that Sir Ramus mentioned, but also partly on ideas that I've developed elsewhere, or just, say, general ideas from the field. And so since I've been trained as a physicist and a philosopher, it will in some parts be very technical, in some parts it will also be very philosophical. And philosophy, for those of you who are not frequently working on it, is often concerned with definitions, and actually definitions will play quite a huge role in this talk. Apologies for that in advance. And I will start this talk by a number of quotes expressing some opinions on its topic. First, some of which probably are very well known in the community. First one is from Arthur Eddington, said that the law that entropy always increases, the second law of thermodynamics, holds, I think, the supreme position among the laws of nature. If someone points out to you that your pet theory of the universe is in disagreement with Maxwell's equations, then so much the worse for Maxwell's equations. If it is found to be contradicted by observation, well, these experimentalists bungle things sometimes. But if your theory is found to be against the second law of thermodynamics, I can give you no hope. There is nothing for it but a collapse in deepest humiliation. Then Albert Einstein, of course, he must be right. Classical thermodynamics is the only theory of universal content concerning which I'm convinced that within the framework of the application of its basic concepts, it will never be overthrown. And then last quote is from an engineering textbook. Together, continuum mechanics and thermodynamics form the fundamental theory at the heart of many disciplines in science and engineering. So quotes like this, and also the opinions that have been expressed before, would indicate that thermodynamics probably is a fundamental theory. Here are some other quotes from the philosophical literature. First one, very short, but we don't think that thermodynamics is a fundamental theory. So that's a statement made within a longer discussion there, which isn't really that much elaborated even within the paper that it's from, because basically the paper is written based on assumption, well, of course, thermodynamics is not fundamental. Who would ever be so stupid to suggest such a thing? And then from Kai Callender, from a paper entitled Taking Thermodynamics Too Seriously, he wrote, but some people, it seems to me, have too much respect for thermodynamics. They take the field from a foundational perspective too seriously. And this taking of the field too seriously is responsible for significant errors in the foundations of statistical mechanics. And so it seems that this is an topic that people have very strong opinions about, and also a topic that people have very different opinions about. And so is thermodynamics fundamental? And one thing to emphasize here that I think might seem somewhat trivial, but that nevertheless is very important, it should be mentioned here. Whether thermodynamics is fundamental depends very much on what you mean by the word fundamental. And those different quotes from the beginning probably are based on different opinions on what it means to be fundamental. So take the engineering textbook first. So they say thermodynamics is fundamental. What they mean by that is thermodynamics is very important. So thermodynamics is fundamental for engineering, means engineers need to know about thermodynamics. And that's probably something that no one would really argue with. So Eddington and Einstein, who don't explicitly use the word fundamental, they probably mean something like thermodynamics is fundamental in the sense of we are very convinced that thermodynamics is correct. So no one would seriously doubt that the second law of thermodynamics is true, and in that sense it's fundamental. Whereas North and Callender, who both say it's not fundamental, what they mean by thermodynamics is not fundamental, they mean thermodynamics is reducible to statistical mechanics. And I think it's, let's say, a general message to keep in mind if you're having arguments like this. It's important to first clarify how you're using certain words. So Tutmore et al. And North, they're not necessarily in contradiction when they say thermodynamics is or is not fundamental. They just mean the word fundamental in a different way. And of course, the question, is thermodynamics fundamental, depends on what you mean by the word thermodynamics. And again, this is something that people can have different opinions on. So thermodynamics was developed in the 19th, perhaps early 20th century as a phenomenological theory that describes macroscopic processes concerned with heat and work. It's an equilibrium theory. There are also many extensions of it that broaden the scope of application, something like non-equilibrium thermodynamics, quantum thermodynamics, stochastic thermodynamics, which are concerned with very different systems that can be out of equilibrium, even active, maybe very small, subject to very strong fluctuations, and these often tend to be microscopic. Or I can mean by thermodynamics something like, well, just a theory that has a certain mathematical structure. So, for example, there are people who apply concepts of thermodynamics maybe in economy or something like that. And of course, that's a way to use the word thermodynamics. But then again, you mean by the word thermodynamics something different from someone who does quantum thermodynamics. And again, this is something very different, important to keep in mind, because when philosophers say something like thermodynamics is not fundamental because it's only an equilibrium theory or because it's only phenomenological, and then the physicists say, well, that is wrong because look at all these papers applying thermodynamics to individual spins or something like that. Then on the one hand, it might be that philosophers sometimes not sufficiently aware of these modern developments in physics, but it can also mean that philosophers just mean the word by thermodynamics something different. Namely, philosophers mean by thermodynamics often at least a macroscopic phenomenological theory, and then these things that physicists do when they do stochastic quantum thermodynamics that would, for a philosopher, maybe count as statistical mechanics. And then again, so when you argue about whether thermodynamics can or can't do something, it's important to keep in mind, what do we mean by thermodynamics? Because that will very strongly determine the answer. Okay, so in this talk, I will not so much focus on the question, what is thermodynamics? And I will also not discuss a lot what the word fundamental can possibly mean. I will just subscribe to a certain definition of the word fundamental. So if you disagree with me, then also that might be because of this definition. My definition is a fundamental theory is a theory that is not reducible. And so what do we mean by being reducible? It's a very generally and widely used theory or concept within the philosophy of science concerning what one might think of as different levels of reality. And so this picture here visualizes this very nicely, and it describes an idea that you might be familiar with, that the world and also the scientific description of the world has different levels. We can look at the world on very large scales and then describe it with biology, psychology. At smaller scales, we need something like chemistry maybe, or biochemistry, and then very small scales, we need something like quantum mechanics, further down, maybe even quantum gravity or whatever. And a general idea, and this idea is known as reductionism, is something like, well, everything that happens on this scale in biology, psychology, and so on, is in the end determined by the things that happen here at this scale. So if I would be able to describe the world completely at this scale on the level of quantum mechanics, then in principle, although probably not in practice, I know everything that happens at this scale. And also causation only works in this way. So everything that happens on this scale is in the end caused by things that happen here at this scale. And everything, let's say all scientific theories describing the world at this scale should in some way be derivable from here. And this is then one thing that might make you think thermodynamics is not fundamental, because thermodynamics is probably somewhere here. And well, it depends then on the things that are further down in this hierarchy, and therefore this thing here is more fundamental because it's the basis for everything that's on top. An even better illustration of this is probably this picture here, which is showing how different fields can be arranged by purity, which also means something like being reducible too. So, you know, if you use sociology, it's just applied psychology, which is just applied biology. You know, if I know all of biology, in principle, I can infer everything that will happen in psychology. Same biology, well, it's basically all reducible to chemistry, right? If I know all the chemistry in your brain, I will in principle know what you think. But what is chemistry? Well, chemistry is basically physics of the the electrons in the atom's orbitals. So in the end, everything is reducible to physics. And then the language of physics, of course, is mathematics, but that's a different story. And so this is a typical idea of reductionism. So here I've boiled it down a bit. It means something like the most fundamental description of a system is the most microscopic one. Everything else is determined in principle by this microscopic description, or philosophers would say it supervenes on this microscopic description. And in particular, all results that you have in some higher level science, so in the science like chemistry or biology, can in principle derive from results from elementary particle physics. Of course, in practice not. I can't in practice predict what humans will do by solving the quantum field theory for all of the electrons a human consists of. That's why I need psychology. But on this kind of idea, that's the only reason that I need psychology. If I were able to solve these equations, and if I would have the initial conditions, then there would really be no need for psychology, because everything is reducible to this microscopic level. And again, so as I said, it depends a lot on definitions. So this idea of reductionism can be used and interpreted in several ways. You can interpret it as a statement about laws of nature and as a statement about science. And you can be a reductionist in one way without being a reductionist in the other way. So when you're a reductionist in terms of about the laws of nature, then you mean something like, well, the laws that hold on the macroscopic level, they are reducible to the ones on the microscopic level. So it's everything that the microscopic laws determine everything else. Or you can think of it as a statement about sciences. So I can say, okay, chemistry is in the end reducible to physics. So coming maybe back to this figure here, I can be a reductionist in the sense that I say everything that happens here is caused by things happening here. Or I can be a reductionist about these theoretical descriptions in a sense, well, this theory here is derivable from this theory, and therefore this theory is less fundamental. Okay, and then the counterexample would be something like emergence. Emergence is generally a word that is used when reductionism in some way fails. And then there are, again, many ways in which something can emerge, or in ways in which reductionism can fail. There is weak emergence, which is probably not very controversial, which means something like at higher levels, there are qualitatively or conceptually new phenomena. So for example, I can have this cup here. Of course, the microscopic laws of elementary particle physics don't know anything about cups or tigers or whatever. And so in this sense, if I go to higher levels, then I find something like cups or tigers. These are conceptually new. And so even though in principle, all the constituents of a tiger are describable by quantum mechanics, still tiger is something conceptually new that you have on a higher level. Whereas strong emergence would say, well, what happens at the macroscopic level is in principle not describable by the macroscopic laws. So it means even if I were able to solve all the equations of the microscopic particles, then I would still not be able to describe what happens at the macroscopic level. So this is a position that nowadays, at least nowadays, probably is not very popular. So at least probably there are very few scientists who would have it. One reason one may have such a position is, for example, if one is a mind-body dualist. So let's say, suppose I believe something like, I as a human have an immoral soul, which is, sorry, not an immoral, an immaterial soul, which causes my behavior. Then I would maybe believe something like, well, I can't predict everything that I do just by solving the equations for all my neurons. Because even if I were to do that, I would still not describe what my soul is doing. My soul is causing at a macroscopic level things that the microscopic level in principle couldn't give you. Okay, and thermodynamics is a very interesting case study for these kinds of things. And because thermodynamics is often thought of as a paradigmatic example for reductionism. So if I take, so thermodynamics is probably a theory, and let's at least for now, let's assume that or to be our definition of the word thermodynamics, that describe the world at a macroscopic level, at very large scales. It describes the T I have in here, but not so much the individual constituents in it. And then it is often believed, well, thermodynamics is a theory that is reducible, because you can derive the laws of thermodynamics from the laws of some more microscopic theories. So for example, the temperature of, which is a macroscopic concept, a concept from thermodynamics, can be identified as something like mean kinetic energy of the particles. And thereby I have reduced thermodynamics with its concept of temperature to something microscopic, namely the concept of mean kinetic energy of particles, and therefore thermodynamics is, on this account, not fundamental. That is based, so this idea was first spelled out, or at least most prominently spelled out in this book here, The Structure of Science by Ernest Nagel, which introduced in philosophy the idea of reductionism, and which also described it explicitly using this example of temperature and thermodynamics thereby being reducible. And now there are several problems that you can have with this idea of thermodynamics being reducible. The first problem, which is a very philosophical one, is the problem of multiple realizability. So this is an argument against scientific reductionism that comes from the philosophy of mind. So in philosophy of mind, reductionism would be the idea that all my mental processes, so all my thoughts and personality and so on, are in the end reducible to what the individual neurons in my brain are doing. And now a problem you can have with this kind of view is that a certain mental kind, by which I mean a mental phenomenon, something like pain, can be realized by different neural configurations. So, I mean, there is the pain of me, the pain of you, there is the pain of a crocodile, there's maybe the pain of a Martian, if such a thing as a Martian exists. And now the problem is that my pain and the pain of a crocodile probably look very different if you really zoom down to what all the individual neurons do. And now the problem is, if I say pain is nothing else than a specific configuration of neurons or a specific state of neurons, then it's a problem if my pain and the crocodile's pain look very different, because then obviously pain is not identical to a certain specific neural configuration. And then the anti-reductionist perspective would be to say something like, Look, of course, when I just look at the neurons, I can't see something that is I and the crocodile have in common. But if you look at our brains on a high level, then you can see something that we have in common, namely pain. And therefore, pain is not reducible to what the individual neurons do. And now, I think in the case of thermodynamics, this is an even better. So thermodynamics is for this an even better example. Because if you think of the statement thermodynamics as mean molecular kinetic energy, that's in almost every system wrong. So it's correct for an ideal gas, but it's wrong, for example, for a photon gas. So in a photon gas, you can't meaningfully speak about something like mean kinetic energy of the particles. But still, a photon gas can have a temperature, and it can be in thermodynamic equilibrium with a gas consisting of little billiard balls. Or black holes, which I will come to even later. They also, we assume, can have a temperature, but that temperature is not something like mean kinetic energy of the particles that the black hole consists of. And that means the temperature satisfies this property of having multiple realizability. And now the thing is, I still would say that this gas consisting of little billiard balls and the photon gas and the black hole all have something in common, namely they have in common that they have a certain temperature. But what unifies this concept of temperature across different systems is not a specific microscopic realization, it's the role it plays in thermodynamics. And therefore, to speak of something like temperature, I need thermodynamics. I can't just reduce it on a conceptual level to the language of language of this microscopic description, because there I couldn't find a unified description for temperature of the photon gas and temperature of the classical gas. Another problem which I had already hinted at is the thermodynamics of black holes, which is a somewhat speculative area of research, but nevertheless a very important and influential one. So you can ascribe to black holes an entropy and maybe also something like a temperature. The equation for the entropy of a black hole derived by Stephen Hawking is a very famous one. You can find even t-shirts where you can have this entropy equation on it. And so obviously we're able to do something like thermodynamics of black holes. So that's a quite substantial area of science. And now the problem is, if I think, well, thermodynamics is something like a description of many particle systems that in the end just comes from the microscopic theory of all the individual particles, then black hole thermodynamics is is difficult to make sense of, because a black hole is an extremely simple object. If you tell me the mass, charge, and angular momentum of a black hole, then you told me everything that one can in principle know about a black hole. A black hole is really just a singularity. It's a really simple object that doesn't have any, in classical general relativity at least, any kind of microscopic structure. And then when I think of entropy as something like disorder in the framework of statistical mechanics, then again, this is a problem, because I mean, a black hole doesn't really have anything like a disorder. It's not that a black hole is in some way more disordered, but a larger black hole nevertheless appears to have a higher entropy. And now here could say, well, of course, that's true in classical general relativity, but what about quantum gravity? So in quantum gravity, what people do have a statistical mechanical description of a black hole. And then in theories like string theory, you can then, and people do that, derive the entropy of a black hole via statistical mechanics. And that then gives you something like this equation from Stephen Hawking. And then people use that even as a test case for these quantum gravity theories. So the problem with quantum gravity is theories are very difficult to test experimentally, to put it mildly, and so you need some kind of other way. And something that people do there is to say, okay, I know that the entropy of a black hole is this and this, and therefore, if my theory of quantum gravity is correct, it should reproduce this equation. And that's a reasonable way to test these theories. But the first thing to emphasize here is what we do then is we use thermodynamics to test statistical mechanics. So we're using, say, on an operational level at least, we test a certain microscopic theory by whether it's compatible with thermodynamics, which means that we're at least implicitly assuming something like Einstein-Eddington did, which means, okay, thermodynamics has to be correct, which means whatever the correct theory of quantum gravity is, it has to be compatible with thermodynamics. And if it's not, then we rule it out. I mean, at least in principle, there's no reason why that should be the case. Maybe quantum gravity isn't compatible with thermodynamics, but we appear to assume that it is. And then second, we can say, okay, well, at least hypothetically, philosophers like to work with thought experiments. We could have a world that has classical black holes, so a world that is just governed by classical mechanics. And in such a hypothetical world, would these black holes have an entropy? I mean, probably they would, because the arguments that you use to derive this equation here don't explicitly use concepts of quantum gravity. And so at least in this hypothetical world, thermodynamics wouldn't require to have some kind of statistical mechanics underneath it. A third problem, which is again more on the theory reduction side, is something like an observer dependence of thermodynamic quantities. So thermodynamics is a theory that works with concepts like heat or work or entropy, and these are quantities that depend often on certain choices of manipulable or observable variables. So we'll speak about this in a more technical way later. But it means, for example, that different observers can have different thermodynamic descriptions of the same systems. So for example, if two people look at two gases mixing, and then one person is able to distinguish the particles that were initially in one half and one person isn't, then these two persons would come to different conclusions about what is the mixing entropy of the system. And the reason is that entropy is a quantity that, being a measure of disorder, depends to a certain extent on what degrees of freedom you track or you don't track. And now some people have brought this up as an argument against the fundamentality of thermodynamics because, well, fundamental theories shouldn't have this property that they depend on the observer. But still something that makes reduction more difficult. So if entropy depends on the choices of the human observer, then I can't reduce entropy straightforwardly to properties of the individual particles because they probably are not observer dependent. And then there is the fourth problem, which I would like to spend the majority of this talk on, because it's the problem that I've thought about the most. And this is the paradox of irreversibility. Now, this problem is concerned with the fact that, as you probably all know, macroscopic thermodynamics has a very clear arrow of time. So macroscopically, entropy can only increase, it can never decrease. And then if you reach the equilibrium state, entropy is maximal and it will always remain maximal. And this is a problem because the microscopic laws of both classical or quantum mechanics are invariant under time reversal. So according to the microscopic laws of physics, everything that can happen in one direction of time can also happen in the other direction of time. So there isn't really a reason why entropy should always increase. And in fact, so if you look at the microscopic definition of entropy in Gibson statistical mechanics, which is it's the trace of rho log rho, then you can show this two-line calculation that this entropy is constant. So rho here is the microscopic probability density or density operator of the system. And that's a problem because, of course, entropy shouldn't be constant. It should increase as long as we're out of equilibrium. It should only be constant in equilibrium. And the way this problem is typically solved in statistical mechanics is via coarse graining. So you say something like, well, I can't observe the system on a microscopic level anyway. I don't know all the microscopic details. So I replace this microscopic description of the system, which is rho, by some coarse-grained or average density rho bar. And then I define the entropy not in terms of rho, but in terms of rho bar. So it looks like this. And this coarse-grained entropy is no longer subject to Liouville's theorem. Therefore, this coarse-grained entropy can increase. So here's an illustration of this. So suppose this water here is phase space, and I put in here, have here some initial state. And then the way this, so this is my density rho. And the way this density rho evolves through phase space is in such a way that its volume is conserved, and therefore the entropy is conserved. So in principle, I can, so if this from here to here is the microscopic time evolution, then this is completely reversible because there is a one-to-one mapping from here to here. But then if I look at this on a macroscopic level where I can't resolve these fine structures here, then it looks to me as if this droplet rho here has increased in volume. And then on a macroscopic level, it's not possible to go back from here to here because I've lost this information about where my initial condition was. And that means that on the macroscopic level, things look irreversible, even though on a microscopic level they are not. And the intuitive explanation for this is using now the framework of Boltzmannian statistical mechanics, that every macro is, well, what is entropy? Entropy is the measure of the number of microstates that a certain macroscopic state can be realized by. And every macrostate of a thermodynamic system corresponds to several possible microstates. So if I look at a gas, for example, then a macroscopic state can be something like it has a temperature of 200 Kelvin. There are many ways microscopically a gas can have 200 Kelvin, and these are the microstates associated to this macrostate. And the equilibrium state, which is the state of maximal entropy, is by definition to some extent the state that has the largest phase space volume. And if a system randomly moves through phase space, then just statistically the most likely thing to happen is that the system approaches equilibrium. And that is the explanation for this macroscopic irreversibility, because it's the most likely thing to happen. More technical example, projection operators. So suppose I start with a microscopic description like this. Helmholtz equations are reversible. I can cause graining by saying the only thing I care about is my macroscopic number density. When based on this assumption, I coarse grain, I get a description like this, which gives me the time evolution of the density in a thermodynamic framework. It evolves to the minimum of the free energy, so it's irreversible. So I got this irreversibility from coarse graining. Now the problem with all these arguments is that the original microscopic dynamics that I started from is invariant under time reversal. So I can say, okay, I replace t by minus t, I replace p by minus p, and then I do the exact same derivation that led me to this theory again, and leads me to this theory. Now, this is a theory that predicts that the free energy will always increase. In other words, that entropy will always decrease. And now that, of course, is a very bad theory because it's completely wrong. But the derivation of this theory has used essentially the same kind of mathematics as the derivation of this theory. So what went wrong? Why did it work in one case and not in the other? And in philosophy, a very typical solution for this is a so-called past hypothesis. And the past hypothesis is based on the idea, well, if there are two ways to break the symmetry of a system, you can do it by the dynamic equations and you can do it by the boundary conditions. And now if the dynamic equations that govern the law of nature don't have an asymmetry between past and future, then it has to be the boundary conditions. And specifically, we assume then that the early universe was in a state of very low entropy, this so-called past hypothesis. And that's the idea, is the explanation for this thermodynamic asymmetry. So at the beginning of the universe, entropy was very low, and that is the reason why it's now increasing. Whereas if the initial state of the universe would have been different, then that would mean that entropy would now decrease. And what that means more mathematically is something like the initial probability distribution or the initial state of the universe was such that it did not have certain special initial correlations. So we can sort of assume that the universe had a certain initial macrostate, impose a certain uniform probability distribution compatible with this macrostate. And then if we make this assumption about initial conditions, then we can find that and we can show that the entropy in the forward direction of time always increases. And we can also show, importantly, that it will always increase in the backwards direction of time. And that means we need to impose this specific initial condition at the beginning of the universe. And that means that it is because this special initial condition of the universe, that's the idea, is the reason that the laws of thermodynamics hold in the way we assume they hold, or we know they hold. And a good argument for this kind of idea is the fact that if you have such special initial relations, then anti-thermodynamic behavior is possible. So, for example, there is this very nice paper here where they did an experiment with spins, and where usually, so you have a hot spin and a cold spin, and usually then heat will flow from the hot to the cold system. But what they showed is if you prepare the system in the right initial state, in the quantum system you can do that, then heat actually flows from cold to hot. And the fact that you can generate exceptions from the laws of thermodynamics by having, so to speak, the wrong initial conditions means that the fact that they usually hold in the way they hold is because of this initial state. And now in philosophy, this framework of coarse graining is sometimes seen somewhat skeptically. And the objection is basically, well, if you replace this microscopic description in terms of this density rho by rho bar, then you're artificially introducing an asymmetry that the actual dynamics doesn't have. And that in some cases, like a so-called spin-echo experiment, leads to something that looks like a violation of the second law of thermodynamics. So more simply speaking, if we say, okay, we explain thermodynamic irreversibility by something like we don't care about microscopic details, which you do if you do it via coarse graining, then that essentially means that the thermodynamic asymmetry only exists because we don't care about microscopic details. But now if I'm wondering why my tea is cold now, or why an ice cube is melting when I put it in the sun, then we would say, okay, well, the fact that an ice cube is melting should not depend on whether I care about its microscopic state. The fact that ice cubes are melting is a fundamental law of nature. And now if I say it's, well, I derive it by appealing to something like microscopic details that I don't care about, but something like coarse graining, then it's a problem so then it can't be a fundamental law of nature. And therefore, interventionists argue, well, the real solution to this problem, microscopic laws are reversible, thermodynamics is not, is that, well, microscopic laws are only really reversible in an isolated system. A real system is never perfectly isolated, and therefore, the approach to equilibrium is a consequence of external perturbations. And now, because of arguments like this, which are probably quite plausible, this idea of coarse graining is very controversial in philosophy of physics. So a very famous philosopher even called it ridiculous and disreputable procedure, and we need probably something like the past hypothesis to explain why there is an asymmetry on thermodynamics. But on the other hand, I mean, a lot of modern physics, and indeed a lot of my own scientific career, is based on this idea of coarse graining. So it probably can't be that ridiculous, I would argue. And also, let's say, if you do use thermodynamics for deriving the diffusion equation, if you do engineering, for example, you're not explicitly appealing to the entropy of the early universe. So if you are an engineer and you use thermodynamics to predict what will happen in a certain heating process, you don't say, well, because of the state of the universe after the Big Bang was like this, this iron will now melt. You don't need general relativity for thermal engineering. And therefore, it's kind of weird to say, well, thermodynamics in the end only holds because of some cosmological arguments. And the solution I would propose to these kinds of problems is to say, well, again, we need to be careful about what kind of questions we're asking. And when we're trying to explain thermodynamic irreversibility, then we need to take into account we actually have a number of very different problems that we need to disentangle from each other. And physicists and philosophers tend to answer these problems in a different way because they ask different questions. So the first one is, I would say, the question, where exactly in thermodynamics is irreversibility located? Now, typically it's argued that this is within the second law. So the second law of thermodynamics is the reason that thermodynamics is irreversible. Now that is difficult because at least in a standard formulation, thermodynamics doesn't really have equations of motion, so it's hard to say where to find an arrow of time. And there is a very nice paper by Johannes Gutenberg, which I forgot to refer to here, which on 90 pages lists a lot of different formulations of the second law of thermodynamics, and asks which ones are equivalent, which are not, and which of these have an arrow of time, which one don't. There's a follow-up paper by Brown and Iffing where they say, okay, the second law of thermodynamics actually doesn't provide you with irreversibility. So we need an additional axiom, which they call the minus first law, which says that every isolated system spontaneously switches to a unique state of equilibrium. The second question is what we mean by equilibrium and entropy. Now, in coarse graining, I said I've defined the entropy via this coarse grain density, and thereby said, well, the equilibrium state is the set where the entropy is with the maximal coarse grain entropy. An interventionist, on the other hand, would define entropy using this fine grain density, implying that in the coarse grain system it is conserved. And now I would argue these two different schools of thought don't actually disagree about any of the physics. They only care about, in the end, definitions. So if I have a completely isolated gas and I have a completely isolated box and have some gas initially in some corner, then it will expand. And both coarse grainers and interventionists will agree that it will expand. And the point is that an interventionist would say, well, the system is not actually approaching equilibrium because even though it has now expanded, it still has the memory of its initial state, and therefore it didn't actually approach equilibrium. Whereas a coarse grain would say, well, in the end, the state is uniform, in the beginning it wasn't, and therefore, of course, the system has approached equilibrium. So they don't agree on any of the physics, they just disagree on the definition of equilibrium. The third problem is how do we justify coarse graining, and why can we appeal to, let's say, the lack of knowledge of human observers when we explain thermal phenomena? They would just say, well, coarse graining is used very successfully in physics, even in cases where you don't explicitly want to explain some kind of arrow of time, and therefore, if as a philosopher you reject the idea of coarse graining, you need a very good explanation for why it works so well. The fourth, and then we are finally coming to sort of the key questions. The fourth problem that is to be solved is why do systems approach equilibrium? If you look at how these derivations actually work, then this is basically this questions, why do systems, given an initial non-equilibrium state, approach equilibrium? And the reason is because you can neglect so-called memory effects. Or in other words, why can we assume that the thing that a system, the way the system evolves in the future depends only on its present state and not on the states it had in the past. And then there is the fifth problem. This is the question, why can we apply our answer to the fourth problem, whatever exactly it was, not in the backwards direction of time? And there the solution is, I would argue, the past hypothesis. And this is the explanation why it's not possible, so why it's not necessary for example, engineers working with the diffusion equation to care about the initial state of the universe, because they're concerned with question 4. They're concerned with the problem, why does entropy increase in the forward direction of time? Whereas if I want to explain why is it this direction, not the other one, then I need to appeal something like the past hypothesis. And that also means that a particular criticism sometimes brought against interventionists is kind of unfair, namely the criticism, well, if you explain irreversibility by external interventions, also this argument you could have used in any direction of time. And then interventionists could say, well, that's true, but interventionism is a way to answer question 4 and not question 5. Okay, how am I doing time-wise? Because you see it's almost at the hour now, the equations will come.
Michael, you can go up to 10 minutes now and leave 10 minutes for question and answer.
Yeah, okay. Okay, then I will explain this at least for some time using a few equations, namely the so-called T2025 formalism. This is a formalism from statistical mechanics, which allows you to start from some microscopic dynamics, get equations of motion holding at a larger scale. So this is a formalism that in this hierarchy picture from the beginning allows you to explicitly get the equations holding at this level from the equations holding at this level. And how this works is the exact microscopic dynamics typically looks something like this. So if this is, for example, the density operator of a quantum system, it obeys this equation here. It's the Liouville von Neumann equation. And the solution is something like this, just formally. And now you do this coarse graining, which you do by defining a projection operator, which, if you apply it to this microscopic density, gives you the coarse grain density. And you also define an orthogonal projection operator, which is 1 minus p. And now I can multiply this equation here by both p and q, which give me these two equations here. This is an equation for the relevant degrees of freedom. So this is an equation for everything at the macroscopic scale. And this is an equation for these microscopic details. And I can solve this equation here formally, and the solution is something like this. I take this equation here and I insert it in this one, and I get this equation. Now, if you weren't able to follow all these details so quickly, it's no problem. Essentially, what I did is I have started from some equations that describe the system on a macroscopic level. So let's say they describe all the individual molecules in my cup of tea. And what I derived is a macroscopic equation, and in particular, an exact macroscopic equation that describes, let's say, just the temperature of the tea. And this equation has 3 terms. This one is a reversible part of the dynamics. This is a memory term, which says that how the system evolves forwards in time depends not just on its state at time t, it also depends on its state at some previous time. And that's the price I have to pay for ignoring these microscopic details. Because in principle, they may play a role. And then there's finally this term, which depends on what were these irrelevant degrees of freedom at the initial time. And then I make 2 assumptions. The first assumption is the so-called Markov assumption, which means that this integral here decays very, very quickly on a time scale in which this is approximately constant. And the second assumption I make is that these initial correlations here are 0. And then I get this equation here, which is called the master equation. And this is, so to speak, the general procedure in which you can obtain irreversible equations at the microscopic level from reversible ones at the microscopic level. So if I want to derive the microscopic equations for why heat flows from hot to cold from the microscopic dynamics where everything is reversible, I need to make something like the Markov assumption, which is I assume that energy evolves slowly compared to other degrees of freedom. And I need to assume that there are no special initial correlations, which, for example, would be wrong in this quantum experiment that I talked about. So where this irreversibility comes from? So to derive the macroscopic irreversible equations, I need to make two assumptions. The first assumption is the Markov assumption, which means that my macroscopic degrees of freedom evolve solely compared to the microscopic ones. That solves problem 4. And then I need to assume that the system starts with a specific initial state, namely that one that has a low entropy, that doesn't have special initial correlations. That solves my problem 5. Okay, now what does all of that imply for my overall question whether thermodynamics is fundamental? So as being said, a typical statement of thermodynamics would be something like there is irreversibility. And when I say thermodynamics is fundamental, I mean something like thermodynamics is not reducible. And you could say, well, you've just done such a reduction, namely you've derived this equation, which is in some sense thermodynamics, from this equation, which is the microscopic part. And what you can say against it are now several things. I would say 2 of them are the main things. The first one is, in moving to this part here from this microscopic description, I've introduced this coarse graining, which is this projection operator P. And the microscopic laws of physics don't tell me what this P here is. So in selecting what my macroscopic degrees of freedom are, something like temperature and so on, I've used knowledge of thermodynamics. And so let's say just within this microscopic description, I wouldn't have been able to do this without any prior macroscopic knowledge. And the second question is, okay, why can I make these 2 assumptions here? That's not at all trivial. So here it's, let's say, at least mathematical difficult to prove it. And here, I would say, it's known that there can be exceptions to this, like this quantum experiment. So it's not trivial why this at all holds. Although this, I would say, is probably a more technical problem in the sense of it shows that thermodynamics is not yet being completely irreducible, which doesn't exclude that at some point it will be. So to some extent, I would then summarize to summarize, then I would argue thermodynamics is a fundamental theory, where by fundamental theory, I mean a theory that is not reducible to the dynamics of individual particles. That has to do with technical problems in actually reducing it, and it has to do with the more conceptual problem that thermodynamics operates with conceptually other notions than microscopic physics does. I explicitly don't claim by this that in any individual thermodynamic experiment, anything happens that is in contradiction to the laws governing these particles. So I don't think that there are exceptions to the laws of elementary particle physics. So I don't believe in strong emergence in that sense. I've talked a lot about irreversibility as well. I've argued it should be understood as a combination of, which is a specific problem of this a specific reductionist problem, because it's a problem of how you can explain macroscopic irreversibility based on macroscopic irreversibility. I've split this problem into 5 subproblems, and I've shown it comes from a combination of slow macroscopic degrees of freedom, that's the Markov assumption, and the absence of certain special initial conditions. With that, I'm at the end. Thanks you again for your attention, and I'm happy to take any questions.
Thank you, Michael. That's really very interesting. Goes to the very details of the why there is a fundamental how it translates from micro to macro, and what are the other things, connection and like irreversibility. That's really interesting. And now I think we would open, like Michael said, to the questions, and I see some of the hands raised. Let's start with Gregory. Gregory, would you mind
Yes,
unmute yourself and ask question directly to
I unmute. I
Michael?
unmute. Are you hearing me?
Yeah, we can hear you.
Yes.
Okay. First, Michael, thank you for your panoramic view. It's really interesting, really impressive. And I have question about absence of initial conditions. Is it correct?
Hmm?
You absence of initial conditions correlation, correct?
Yeah.
But you know, in my chemical kinetics, we always have this correlation because mass conservation law, you know, what to do. But if we have irreversible process to equilibrium, but initial conditions always have this limitation, mass conservation law.
Yeah, but so by correlations, I don't mean something like mass conservation. So conservation laws are something that you would probably use for showing that the Markov assumption holds. So to speak in the language of chemical kinetics, if you derive the Boltzmann equation, which is an irreversible equation because it has an H theorem, then you assume something like, well, particles that collide are not correlated before a collision. You know, they just come from random directions.
Okay.
And the question is, why do I make the assumption that they are not correlated before a collision? I could also assume that they're not correlated after a collision. And then if I were to make this assumption, then I would get the time reversal of the Boltzmann equation.
Okay,
and so this assumption, go ahead.
In this case, we need to distinguish what kind of correlations we have. Micro correlations, macro correlations, what kind of correlation?
Yeah, absolutely. I mean micro correlations.
Micro correlation. Okay. Yeah. But if you don't have collision, for example, process solid body, there is no collision, it's not gas. What is this case? What is correlation, initial correlation? Interaction between some units.
Yeah, so what it means in a particular experiment depends on the details of that experiment. But the basic idea is more something like, so in principle, whatever irreversible process you have, the time reversal of that process is also allowed by the microscopic laws of physics. And then why do we not observe it? And in principle, if you have any chemical physical experiment that is irreversible, and you take the final state of the system and then reverse the momenta of all particles, then you would see entropy decreasing. So you would see the time reversal of that process. But the problem is you can't exactly reverse the momenta of all particles in a chemical experiment. And if you were able to do that, then you would get these special initial correlations.
Yeah, but but what do you think? We have experiment from different initial symmetrical conditions. Do you have envisioned such experiment, like to have battery of experiment? One is from specific initial conditions, another from symmetric initial conditions. What will be in this case?
Yeah, so how do you specify your initial conditions?
It's imagine I have reaction A goes to B, just simple reaction. And I have two kinds of initial conditions, A equal 1, B equals 0, or B equal 1, A equals 0. And I have two experiments. non-steady experiment, and what do you think about this experiment from different initial?
Yes, so these would be different initial macro conditions. What I mean is initial. So what I mean by special initial conditions is an initial condition that you can't specify by just talking about the initial degrees of freedom, by the macroscopic degrees of freedom. So in this case, so in your case, the macroscopic degrees of freedom would be something like the concentration of species A and the concentration of species B.
Exactly.
Yeah, and specifying, and so any initial condition that I can specify in terms of species, that many particles of species A and that many particles of species B would not be a special initial condition. A special initial condition would be something like, well, the first molecule is here and has this momentum. The second molecule is here and has this momentum. The third molecule is here and has this momentum, and so on. It's an initial condition that you can only describe like this. That would be a special initial condition. And this is something you typically don't have in chemical experiments because you can't manipulate it that fine.
So when I talk about concentration, I'm among macro conditions.
Yes.
Okay.
Thank you, Gregory.
Okay.
Let's go to the next question. Sripad, Sripad, can you please unmute yourself and ask directly to Michael?
Yes. Thanks for this insightful talk, which actually prompted me to ask two questions related to the theme regarding why thermodynamics is fundamental. So my first question is if we were to make a comprehensive study of why thermodynamics laws are fundamental, I believe it may also be necessary to make a comprehensive study on also the violations of the second law. Now, what exactly I mean by violation is the fluctuation. And these fluctuations addressed, for example, by the fluctuation theorem can occur both in time as well as in space also, which might explain actually the role of gravity as well, the fluctuations in space. So maybe can you please give some maybe some advice regarding how to integrate these fluctuations with the understanding of why thermodynamics is fundamental, fluctuations in terms of violations of the second law?
Yeah, so by violation of the second law, I think it means something like, okay, on average, systems will go towards equilibrium, but because it's a statistical theory, it can also evolve away from it. So I think this is perfectly compatible. So even if there are fluctuations away from the second law of thermodynamics, then it still on average holds. Let's say it's still true that on a macroscopic level, the laws of thermal systems approach equilibrium. That then brings me to the initial question of what exactly do I mean by thermodynamics. So if I think of thermodynamics as the macroscopic theory stating that entropy always increases, then thermodynamics states that entropy will always increase, and then these fluctuations are violations of the second law. Whereas then if I go to more modern versions like stochastic thermodynamics, so stochastic thermodynamics, these fluctuations play a very important role. So it is about these fluctuations to some extent. And there then you would have, let's say, more statistical versions of the second law, and for these statistical versions, a fluctuation is not a violation of the second law. It's just something that this statistical second law would predict. You. There are fluctuations like this, there are fluctuations like this. On average, it's like this.
Okay, maybe I'll think about your answer, and maybe if I have a counter question, I will send you an email. But let me go to my second question. The second and the last question is regarding, in your talk, you did mention about the least action principle and its application to conservative systems. But here actually, I think I have a doubt that the least action principle, which is a variational extremal principle, in fact, it should be applicable to dissipative systems as well. And that is where actually the second derivative of entropy might play a role, and it may link with the maximum entropy production. So any maybe advice or any comments on this use of this least action principle to dissipative systems, and then trying to explain that yes, once least action principle is also extended to dissipative systems, is one step ahead in making thermodynamics fundamental.
Where did I mention the least action principle in my talk?
Somewhere in your talk, maybe it was just in passing that you mentioned that least action principle as applied to conservative systems. But I have a point that, in fact, in 2019, I did publish a paper in Journal of Non-Equilibrium Thermodynamics, and tried and made an attempt to prove that it is also applicable to dissipative systems. And that is where actually the second derivative of entropy plays a role in terms of the extending the least action principle to dissipative systems. And this is where actually I wanted your insights on how fundamental it would be to extend the least action principle to dissipative systems, and maybe that has a link with making thermodynamics fundamental further.
Sripad, I think it was me who mentioned the least action principle with the conservative system, and I think I'll get back to you. And I'll look at the paper as well and try to learn more. But right now, I would like to give time to Bob Evans and then Chris Jens. First, please, Bob, can you unmute and ask question to Michael, please?
Hi, Michael. Good talk. You know me very well, right?
Yeah, thank you.
Could we go right back to the beginning, Michael? I mean, your question is thermodynamics fundamental? And you hinted at the beginning that, I mean, there may be contradictions or possible contradictions between statistical mechanics and thermodynamics. So let's home in on explicit examples. You know, you might say that thermodynamics is to do with macroscopic variables, which it is. But what is amazing is when you use the ideas of thermodynamics, the constituent equations, some rules that are in there, even to situations where, say, liquids, and you've worked on this yourself, are confined to microscopic dimensions in very narrow nanometer or even less pores. The laws of thermodynamics, the equations of equilibrium, I'm only talking about equilibrium, work down to amazingly small dimensions. Could you comment on this? Is it important? But doesn't it show that statistical mechanics is just simply consistent with thermodynamics? Or is there more to it?
So I would definitely agree with you. And maybe I could. So you're familiar with this thought experiment of if there are. So if I would look up many theoretical physicists in a room that have never seen anything of the real world, would they be able to predict that a fluid exists, just given the microscope?
Yeah, I've written about that in many articles, Michael.
And then I would say, so this question, is thermodynamics fundamental, could be rephrased as, if I look up many theoretical physicists in a room and give them nothing but the microscopic laws of quantum mechanics, so the microscopic laws of classical mechanics, would they be able to predict something like thermodynamics?
I think you mean phase transitions.
Yeah, for example, phase transitions or irreversibility or something like that.
No, we're not yet talking about irreversibility.
Okay. Yeah,
We're
then
talking
let's say
about
phase
stable phases of matter.
Mm. And
please,
that I
please
think,
go on. Yeah.
yeah, and I would say the answer to that question would to some extent determine whether equilibrium thermodynamics is fundamental in the sense of not being reducible. And I think it's a very question that is very hard to answer. And then concerning these example of applying thermodynamics to confined fluids. So I definitely agree that's probably an even better example than these black holes, which are somewhat speculative. Because it's something where you have a theory that was originally developed to apply to very large systems, but then found to also apply to very small systems. So it appears to be generalizable beyond the context it was originally developed for. And when we actually do the physics of these systems, then at least on an operational level, we always work under the assumption, well, the laws of thermodynamics will be true for these systems.
Yeah. I mean, a hard man would say this is a silly thing to do. Yeah.
Yes, exactly. But and the fact that a man would say that is an indication, I think, that thermodynamics is fundamental in at least some sense of the word fundamental.
But could I press you? The fact that the rules of thermodynamics actually work down to microscopic dimensions. Let's forget quantum mechanics for the moment. Let's stay classical, but working at a small length scale. The fact that these laws work, or the equations resulting from these laws work, is that not a big deal?
I would say it is a big deal.
Yeah. But I would say this is an example which simply says thermodynamics is fundamental.
Yeah, so fundamental in the sense of being universally. So let's say to come back to this list
working
of beings of fundamental, in the sense of being universal.
Yeah.
So in the Einsteinian sense of being fundamental, so to speak, it always works.
Precisely. No, you put it very well. Yeah. Thank you, Michael. Many thanks. Yeah.
Yeah. Thank you.
Next, Chris Jens. Can you please unmute yourself and question directly to Michael, Chris?
Yeah, Michael. I've been in contact previously. Now, the thing is that your talk was starting from the assumption that statistical mechanics is fundamental, and can we get thermodynamics out of it? Okay, fine. And you showed with very fancy tricks that you can, but you can only do that provided you put some extra assumptions in.
Yeah.
Okay, so it's clear that thermodynamics is not reducible to statistical mechanics. And your discussion with Bob just now confirms that. So there's another attitude that one can take, which is to say, well, universal observation, universal experience shows that all processes are irreversible. So where does that get us? Isn't that another way to proceed?
Yes, definitely. So let's say to some extent that relates to Bob's question. So I've interpreted the word fundamental in a very specific way in this talk, namely as not being reducible, which has to do with you need these extra assumptions for deriving it. But you could also interpret the word fundamental as being universally valid. It is also a very reasonable way of using the word fundamental. And then if that's the way of your way of interpreting fundamental, then the fact that it appears that you get irreversible processes everywhere, and then you observe thermodynamics to be valid on all sorts of length scales and in all sorts of processes, is then the criterion for thermodynamics being fundamental. And would argue it is fundamental also, or maybe even more, on this particular kind of interpretation.
Thank you.
Thank you.
Next, we have, let me go to the screen. Some reason I'm missing it. Next, we have Charles Hall. Charles, can you please ask directly to Michael, please?
I don't know where my video went, but anyway, I'm not a physicist, so I may not understand you precisely, but I have two questions. One, have you extended your boundaries sufficiently? And second, to set up the initial conditions in which you think the laws of thermodynamics are violated, doesn't that require some kind of Maxwell's demon? And I think you will recall the discussion of Maxwell's demon, who could sort out faster moving and slower moving molecules, but the energy required to maintain that information means that the second law wasn't violated after all. And wouldn't the same concept apply to the example that you were putting forward? In other words, I'm extending the boundaries in requiring the information for the initial conditions that you were not assigning a cost to, I think.
That is a very good question. So yes, in principle, I can. So yes, so these special initial conditions would be exactly the kind of conditions that you would usually need a Maxwell demon for. And then the question is, if I have such a situation, and let's say these experimentalists in the example with the quantum correlations would certainly be maybe a kind of human manifestation of a Maxwell demon. And now in their paper, they don't write that what they did is a violation of the laws of thermodynamics. And I mean, having stated that thermodynamics is fundamental, I would agree to them. They just say, well, so we need to, in this specific experiment, we need to take into account in our thermodynamic considerations the information about these special initial conditions. And if you do that, then you can restore the second law in some kind of generalized way. And then if you do that, it's certainly true that then the second law of thermodynamics continues to hold. So it's again, to some extent, a question of what do I mean by thermodynamics? Do I mean by thermodynamics the statement that heat always flows from hot to cold, then it holds only under restricted assumptions? Or do I mean by thermodynamics something more general that may incorporate also thermal aspects of information theory? And then it will probably hold even on a more general level.
I am relieved.
Yeah. Yeah. Glad to hear that.
Unmute, Ram.
Thank you. Michael, thank you for the talk and your thoughts about this topic. I find that, yes, you, of course, had to focus on some specific understanding, a well-defined meaning of the word fundamental to traverse this topic. However, I was thinking maybe the way you defined the word fundamental has a sort of arrow, a certain attitude in it, because often physicists find attractive to look in this stack of, in your slides, you have this nice stack of different scales as a way that the physics is a way to dissect, nature down to quarks and so on. But there is also a reverse error when we are actually interested to describe nature not in a way down to little details, because, well, probably today everyone would agree that it's impossible to describe very complex systems from molecules up to very large scales. And then from the thermodynamics, if you look at the other side of the stack, might be fundamental in the sense that it's a theory that provides us with tools to dissect the nature to larger scales, where we actually look in not dissecting very elementary constituents of matter, but we actually want a theory that describes physics at large. Thank you.
Yeah, thank you. I definitely agree. So if I interpret thermodynamics fundamental in the sense of being universal, or in the sense of being very important, then of course I would say it's probably even less controversial that thermodynamics is a fundamental theory. And I agree also that this view of a layered reality is something that comes with a certain attitude that is probably very popular among physicists, even though there are some problems to this attitude. And so the reason I spoke to this about this at such length is precisely that I think it's important to be explicitly aware of this attitude, because only if you explicitly give a name to this attitude instead of reductionism, and then discuss, okay, is this a plausible attitude to have or not, then you can start realizing to what extent it might be not a reasonable attitude to have. And to what extent maybe it is also.
Yes, thank you.
Thank you.
It seems like we don't have any more questions. Therefore, maybe it's time to wrap up our session today. We really appreciate Michael having time and talking to this interdisciplinary group we have here. You might see that we have a range of scholars here, talking at some social scientists, some thermodynamics, and some physicists. But the strength I saw in your talk is in order to advance from the current stage of the knowledge, we need to kind of combine the strength of physics and the philosophy of science. The later, we try to neglect some way nowadays, but I really feel like the philosophy of physics can have a very important back and forth relationship with the physics. And that's the other reason I was really interested to invite you here. And I think most of us enjoyed your talk and probably learned one or two things more from the previous stage. I really appreciate your time, and for other participants here, probably it'll take about a week for us to process this presentation, and we'll come back with its recording and send you a link of a YouTube. Stay tuned for another email for the recording of this talk. And with that, Eduardo, do you have any other things to add?
No, nothing to add, but just to thank everyone to be again here in this webinar session, in this interesting discussion about the thermodynamics and its fundamentality, So thanks everyone for being here again,
And with that, let's thank and let's give Michael a big clap, and we conclude this 2025 webinar talk today. Thank you, Michael.
Yeah, thanks a lot for the invitation and for coming.
Thank you all, and we'll update you when we have a next speaker. Thank you all.
Thank you. Bye-bye.
Thank you, Gregory. Thank you, Jian. Thank you, everybody. Thank you, Yazda.